So we will talk about principal ideal. I told earlier in a ring the ideal generated by a single element is a principal ideal. Now we shall consider the ideal generated by a non-zero element A in a commutative ring R. So in a commutative ring R, the set AR which contains the elements A into R, where A is an element of R and R is an element of R, is an ideal of R. We have to see that in a commutative ring R, and A is a non-zero element of R, the set containing all the products A and R is an ideal of R. So to show that the set is an ideal of R, we have to show that for any xy contained in R and x minus y is contained in AR, and also x into y is contained in AR. So here in the first para, we have shown that the set A into R is non-empty as 0 is contained in AR, and in the next lines we have taken x is equal to AR for some R contained in R and y is equal to AS for some S contained in R. Then considered x minus y, which can be written as A into R minus R. So it is also contained in A into R as R minus S is contained in R. So we have x minus y is contained in AR. Also xy is equal to A into ARS, which is again contained in AR. Hence AR is an ideal in R. Now suppose if Z, the set of integers, is in R, or if R is a commutative ring with unity, then we can see that for any n contained in Z, n dot 1 is contained in R, where 1 is the unity of R. So we have A dot n is equal to A dot n into 1, which is contained in R, and hence we can see that the set AR is equal to AR plus AN, where R contained in R and N contained in Z is an ideal of R. And of course this is always equals to the above mentioned the set AR. Now we move to a theorem, very important theorem. In a commutative ring R with unity, an ideal M is a maximal ideal. An ideal M is a maximal ideal if and only if R by M is a field. So the proof follows in a simple way. It has two parts. One is when M is a maximal ideal, we have to show that R by M is a field. And conversely, when R by M is a field, we have to show that M is a maximal ideal. So let us take M as the maximal ideal in the first case. So we list the given things. Let M be the maximal ideal of a commutative ring R with unity, that is 1 contained in R. We have to show that R by M is a field. As R is a commutative ring, R by M is also a commutative ring, and as 1 contained in R, 1 plus M, that is 1 bar, is contained in R by M. So R by M is also a commutative ring with unity. To show that R by M is a field, we need only to show that all the non-zero elements form a group under multiplication. That is, we have to show that every non-zero element in the field R by M has a multiplicative inverse. So let us consider one non-zero element x bar contained in R by M. We have to show that X bar is invertible, that is there exists some other element in R by M such that their product is the unity of R by M. Here the unity of R by M is 1 bar, that is 1 plus M. So let us consider X bar as the non-zero element of R by M. That means X is not contained in M but X contained in R. In other words, X contained in R minus M. Now consider the ideal generated by X, that is we write it as XR. The ideal generated by X, that is XR, which is nothing but the set of all those elements of R in the form of X into R. XR is an ideal of R containing X. Hence we can see that M plus XR is also an ideal of R, because we have seen that in a commutative ring or in any ring, if A and B are ideals, then A plus B is also an ideal, where the first element is from the set A and the second element is from the set B. So here also M is an ideal, XR is an ideal, so M plus XR is an ideal. As X is not in M, and 1 contained in M plus XR, because this is M is the maximal ideal and M plus XR is an ideal containing M. So M plus XR is an ideal containing M. As M is a maximal ideal, it implies that M plus XR is equal to R. So M plus XR is an ideal of R containing M, and as M is a maximal ideal, this M plus XR is equal to R itself. And as R is a ring with unity, 1 is contained in R, so 1 is also contained in M plus XR. That means there exists some M contained in M and R contained in R, such that 1 is equal to small m plus XR, where small m is the element of M. You can add the set M on both sides, so 1 plus M is equal to, you can write it as M plus XR plus M. But addition is commutative in R, so XR plus M we can write. Hence 1 plus M is 1 bar, which is equals to XR plus M, or we can write it as X bar into R bar, X bar into R bar, which is contained in R by M. Both X bar is in R by M and R bar is also in R by M. Thus, for every X bar in R by M, there exists some R bar in R by M, such that 1 bar is equal to X bar into R bar is contained in R by M. So here 1 bar is the unity of R by M, and X bar and R bar are elements of R by M. Of course, X bar is nothing but X plus M and R bar is nothing but R plus big M. Thus, every non-zero element, say X bar in R by M, has a multiplicative inverse, that is R bar, such that 1 bar is equal to X bar into R bar. Hence, R by M is a field. So, this proves the first part of the theorem. For the next part, where you consider R by M is a field, and we have to show that the ideal M is a maximal ideal. Here, you need not worry about to show that M is a ideal. It is given M is an ideal. What you have to show? If R bar M is a field, then M is a maximal ideal. So you can note that R by M is a field, so it has at least two elements. One is the unity and another one is 0. So 1 bar is the unity of R by M and 0 bar is the zeroth element of R by M, and also 1 bar is not equals to 0 bar because it is a field, so it has at least two elements. As 1 bar is not equals to 0 bar, that means m is not equals to r, and 1 is not contained in m. Suppose J is an ideal containing m. Suppose J is an ideal containing m. To show that m is a maximal ideal, we have to show that either m is equal to J or m is equal to m is equal to J or J is equal to R. So suppose that m is not equals to J, and choose A contained in J such that A is not contained in M. Choose some element A contained in J such that A is not contained in M. Then A bar is not equals to 0 bar. So A is invertible in R by M. A bar is not equals to 0 bar means A plus M is not equals to M. That is there. So because A is not contained in M, A plus M is not in equal to M. So A bar is not equals to 0 bar. So A bar is invertible in R by M. A bar is an element of R by M which is invertible, that is the inverse exists. So suppose that B bar contained in R by M is an inverse of A bar, hence 1 bar is equal to A bar into B bar. That implies 1 plus M is equal to A into B plus M. Or in other words, 1 minus AB is contained in M. 1 minus AB is contained in M. And this implies 1 minus AB is contained in J, because M is a subset of J. So 1 minus AB is contained in J. But J is an ideal containing A. So for any B contained in R, AB is contained in J. So 1 minus AB as well as AB are contained in J. So if you take the sum 1 minus AB plus AB, it is also in J. That means 1 is contained in J. Now J is an ideal containing the unit element of R, and hence J is equal to R itself. So we have, if there is an ideal J containing M, then either J is equal to M or J is equal to the ring R itself. That means M is the only biggest proper ideal of R. That is, M is the maximal ideal of R.